About 1.4 billion kilometers away from Earth, orbiting Saturn, there is a moon called Titan. Hidden deep within the darkness of the solar system, this world appears at first glance to be nothing more than a thick, orange haze. But once you descend beneath that veil, what emerges is a landscape that, in some ways, resembles processes we know from our world, while being fundamentally different in composition. Icy terrain shaped by liquid flow, vast seas of hydrocarbons and weather systems driven by unfamiliar chemistry. This is not just a frozen moon. It is a natural laboratory that may help us understand how complex chemistry, and possibly the precursors of life, can emerge under very different conditions. So the question is inevitable. Could life exist on an entirely different chemical foundation? For decades, Titan remained a mystery. When observed through telescopes, it revealed no surface details, only an opaque orange atmosphere. Much like Venus, Titan kept its surface hidden behind dense layers of haze. Scientists could only speculate about what lay beneath. That uncertainty lasted until 2005. As part of the Cassini mission, the probe entered Titan's atmosphere and achieved a historic milestone. During its approximately 2.5-hour descent under parachute, it transmitted critical data about temperature, pressure, wind, and atmospheric composition back to Earth. This marked the first controlled landing on a body in the outer solar system. When Cassini reached the surface, it sent back the first direct images of Titan, and the results were striking. The landscape showed features reminiscent of erosion and fluid flow, including branching channels and rounded ice blocks. However, the processes responsible were not identical to those on Earth. The liquids involved were not water, and the rocks were composed largely of water ice, hardened by extremely low temperatures. With this mission, Titan transformed from a distant mystery into a directly studied world. Titan has a diameter of about 5,150 kilometers, making it one of the largest moons in the solar system, larger than Mercury by diameter, though less massive. But its true uniqueness lies not in its size, but in its atmosphere. The surface pressure on Titan is about 1.5 times that of Earth. This dense atmosphere shrouds the surface in a thick orange haze. Sunlight is strongly scattered and partially absorbed before reaching the ground, leaving the surface dimly lit by diffuse, orange-tinted light. As a result, visibility is limited, and the environment resembles a muted, twilight-like setting. The atmosphere is composed primarily of nitrogen, similar to Earth, but the second most abundant component is methane. This leads to one of Titan's most distinctive features. Instead of a water cycle, Titan has a methane cycle. Methane can evaporate, condense into clouds, and fall as precipitation. Over time, this cycle contributes to the formation of surface features such as channels, lakes, and seas. However, these liquids are composed of methane and ethane, not water. This makes Titan exceptional. It is the only known body in the solar system besides Earth where stable liquids are present on the surface. However, this similarity should not be overstated. Titan's surface temperature is around minus 179 degrees Celsius. Under these conditions, water behaves as a solid structural material. Ice forms the bedrock of the landscape, playing a role similar to rock on Earth. The combination of low gravity and a dense atmosphere leads to different surface dynamics. Winds can transport organic particles, forming large dune fields over time. These dunes resemble terrestrial deserts in shape, but differ significantly in composition. In the polar regions, large liquid bodies, such as the Kraken Mare, Ligeia Mare, and Punga Mare, provide strong evidence that hydrocarbons can remain stable on the surface over long periods. These liquids participate in an active cycle involving evaporation and precipitation, contributing to ongoing surface modification. Titan is not geologically static. The relatively low number of impact craters suggests that surface processes, such as erosion, deposition, and possibly cryovolcanism, have altered the landscape over time. Beneath the surface lies another important possibility. Measurements indicate that Titan may contain a subsurface ocean, beneath its icy crust. This ocean is thought to consist primarily of liquid water mixed with other compounds, existing under high pressure at depth. At this point, Titan becomes more than just an unusual moon, because the key question is this: is life limited to environments like Earth, or can complex chemistry, and perhaps life, emerge under entirely different conditions? That question turns Titan from a distant object into a key, because by studying this cold and mysterious world, we may be taking one step closer to understanding how life first began on our planet. What makes Titan truly important is neither its size nor its surface lakes. The real significance lies much deeper. Titan is an environment that helps us test under what conditions the phenomenon we call life could emerge. First, we need to be clear. There is currently no confirmed evidence of life on Titan. This point is sometimes exaggerated in public discussions, but the scientific reality remains unchanged. What we have are only data, models, and a set of intriguing signals that require careful interpretation. Yet precisely for this reason, Titan is considered so valuable in planetary science. Because these signals are not random, if interpreted correctly, they may offer insights into the fundamental conditions required for life. The reason scientists focus on Titan is relatively straightforward. Several key ingredients thought to be important for the emergence of life are present there: a dense atmosphere, complex organic molecules, and environments where liquids may exist, both on the surface and potentially beneath it. This combination played a critical role in the early history of life on Earth as well. However, Titan's conditions are not identical to Earth's, far from it. They are significantly more extreme and restrictive. The biggest limitation is temperature. At approximately minus 179 degrees Celsius, chemical reactions proceed extremely slowly. This makes it very difficult for the type of biochemistry we know to operate in an active and sustained way. In other words, although Titan contains some of the necessary ingredients, the rate and manner in which they interact are fundamentally different from those on Earth. For this reason, scientists mainly consider two broad possibilities. The first scenario involves the potential existence of a subsurface ocean beneath Titan's icy crust. This ocean is thought to be primarily composed of liquid water and would exist several kilometers below the surface, where conditions are more stable than on the exterior. If internal heat or chemical energy sources are present, the possibility of microbial life cannot be completely ruled out. However, this remains hypothetical, as no direct evidence has yet been observed. The second scenario is more radical. If life does exist on Titan, it could be fundamentally different from anything we know on Earth. This is because the dominant liquid on the surface is not water, but methane. This raises an important question. Could life use methane instead of water as a solvent? At first glance, this idea may seem highly speculative, but it has not been dismissed entirely. Some theoretical studies suggest that Titan's chemical environment could, in principle, support alternative biochemistries. Interestingly, certain measurements taken in Titan's atmosphere have shown unexpected behavior compared to theoretical predictions. However, caution is essential here. Such anomalies do not automatically imply the presence of life. In science, the guiding principle is clear: extraordinary claims require extraordinary evidence. And for Titan, such evidence does not yet exist. In summary, the scientific picture is clear. Titan may represent a potentially habitable environment, but there is currently no confirmed evidence that life exists there. Most observations can still be explained through known physical and chemical processes. But the real importance of Titan is not limited to this question. Titan forces us to reconsider a deeper one. How does life actually begin? On Earth, we still do not fully understand the detailed pathway that led from simple chemistry to living systems. What we do know is that at some point, simple molecules existed, and over time increasing complexity emerged. When we look at Titan, we see a superficially similar progression, but under completely different temperatures, chemistry, and environmental conditions. That is why Titan is not an answer, it is an experiment. And perhaps the most critical question is this: if there is no life here, why not? Studying Titan's strangely familiar, yet alien world solely from a distance is no longer enough. To truly understand its river channels, icy landscapes, and possible cryovolcanic structures in detail, we need a mobile explorer capable of moving freely across its surface. The most innovative mission NASA has developed for this purpose is the Dragonfly mission. Unlike traditional wheeled rovers, Dragonfly is a nuclear-powered 8-rotor drone designed to fly through Titan's dense atmosphere. Thanks to Titan's low gravity and thick atmosphere, the vehicle can take advantage of flight in a way that would be impossible on most other worlds. Expected to arrive in the mid-2030s, this explorer will not be limited to a single landing site. Instead, it will fly between different regions, analyzing geological formations and impact craters in situ. Dragonfly will also collect surface samples to directly investigate how complex organic molecules interact in Titan's environment. So what do all these discoveries actually tell us? Titan stands as one of the clearest examples that physical processes in the universe can operate in radically different ways from what we are familiar with on Earth. A methane-based cycle in a freezing world demonstrates that biology is not necessarily confined to the water-based rules we know. The presence of rich organic chemistry on the surface, combined with the possibility of a hidden subsurface ocean, makes Titan a unique natural laboratory for chemical evolution. If Dragonfly detects any signatures related to prebiotic chemistry, especially in regions such as Selk Crater or along the shores of its calm hydrocarbon seas, it would mark a turning point not only for our understanding of Titan, but for our entire view of life in the universe. Titan may be a distant mirror of Earth, but not in the sense of being identical. Instead, it reflects something deeper. What nature can achieve when the same physical laws operate under entirely different conditions. It shows us not only a possible glimpse into Earth's distant past, but also what might be possible elsewhere when environmental limits are pushed to extremes. As this journey comes to an end, one final question remains. If complex structures can emerge even in such an alien environment, what other surprises might be waiting around the countless stars scattered across the universe? Understanding Titan may ultimately mean understanding the universal potential of life itself. If you've watched this far, you've only seen a small part of what the universe has to offer. There's still so much left to explore, and many questions waiting for answers. If you enjoyed this video, consider liking it and subscribing to the channel for more deep dives into space and science, because this journey is just beginning.